Pressure. Okay, in this lesson, pressure. Okay, so we know that pressure is force divided by area. Okay, the larger the force, the greater the pressure. The larger the area, the smaller the pressure. Okay, so if somebody starts stabbing you with this, okay, there'll be a fair pressure. If they stab you with a nail, greater pressure for the same force. Okay, the smaller the area, the greater the force. The greater the pressure, the greater the force, the greater the pressure. Pressure directly proportional to force, pressure indirectly proportional to area. Unit, okay, so unit, well, it's a Newton divided by meter squared, or newtons per square meter, but we call that a Pascal. And we have to be able to define a Pascal, or we just put in the numbers. So we say 1 Pascal is when a force of 1 Newton is on an area of 1 square meter. Okay, that's it. Okay, and we that same kind of carry on in a few other places. Okay, like the definition of Newton and so on. So make sure when you're doing your definitions, you're happy with that. Okay, nothing too dramatic about it. Okay. Next thing we want to look at is Archimedes Principle. Okay, Archimedes Principle. And Archimedes Principle is to do with what happens when a body goes into a fluid, and we'll talk about water. Okay, but before we do that, I want just to remind ourselves of force diagrams. If I have a table and I have a block, a body on it, okay, there's going to be a force down, force of gravity. There's also going to be an equal force up, which we could call the upthrust, okay, but it's normally called the reaction. Okay, and the weight and the reaction are the same because the body is at rest, so the net force must be 0. We're happy with that. Let's take a situation, okay, and this is just a thought experiment now. Let's take a situation, I'll move over here, okay, where I get a beaker of water, but I imagine a scenario where we can take a little cube of that water and maybe colour it red and just concentrate on that little cube, okay? So this is what you call a thought experiment now, just keep you thinking, okay? So basically, I've taken a cube of water there. Now that cube of water is sitting in the water. It's not moving up and down. We've no convection currents or anything like that. So if you think about it, exactly the same time, it's at rest. So it's got a weight down, and it's got a reaction force up, which is equal to the weight. When you're talking about water, we talk about that being an upthrust. Okay, so weight is equal to the upthrust. The name we use is upthrust when we're doing Archimedes Principle. It's also called the buoyancy, and it's also, as we see why, called the apparent loss in weight. Okay, now the weight here is equal to the upthrust. Okay, we're happy enough with that. Right, so if we look at the top here then, so we'll still have that diagram there. Right. Let's take a situation now where we put an object, let's say an iron cube instead of that. So we're taking out our little imaginary cube of water and we're putting in an iron cube. So this is your iron cube. Okay. Now the upthrust will still be there. Okay, the upthrust due to the water will still be there. Okay, it doesn't matter whether there was water in the little cube or iron. That upthrust will still be there. Okay, and that'll also be the weight of the iron cube, which will in this case be greater than the upthrust, okay, because the weight of that amount of iron is greater than the weight of that amount of water. So overall, what will happen is it'll accelerate downwards, okay, but the upthrust will still be there, and its weight will appear to be less than it is. Its weight will appear to be its actual weight in air minus this upthrust, okay. So this is what Archimedes' principle states, okay. There appears to be a loss in weight, and if you look back to this, there's an apparent loss in weight on any body placed in the fluid, and that apparent loss in weight is called the upthrust, and it's equal to the weight of the water that was taken out to replace it. That's Archimedes' principle. The apparent loss in weight is equal to the weight of the water or the fluid displaced. That's it. Okay, now we're going to look at an example of how to describe it. Okay, and all you need to remember for Archimedes' Principle really is the definition and this description. But I think, have a look at this. This is just kind of extra stuff. You won't be asked to be talking about imaginary red cubes, okay, but I just want you thinking. Okay. Oops. Okay, so we'll have a look at the experiment there now. Okay, so let's have a look. I've drawn it in. Okay, so effectively, when you're drawing diagrams, everything's labelled all of the time. Okay, I'm taking liberties with regard to that. So Newton balance and let's say an iron block. Okay, the Newton balance weighs the iron block and gives you the weight of it. If I put the iron block into the water, okay, right, let's think about it. Okay, so this is the weight of the iron block. The weight of the iron block is still the same over here, but there is an upthrust here. We know there's an upthrust, and we know that that upthrust is equal to the weight of the water displaced. Okay, because if you put water back in here, and that would be that amount of water, if you put water back in there, upthrust would be equal to the weight, because the water wouldn't go up and down. Now what will happen clearly here, if there wasn't a string, would be that the object will accelerate downwards, because the net force will be down. But in this case, let's look at values. Okay, so if you did this experiment, let's say you get a force here of 15 newtons, so the weight of the iron in air. Here, okay, let's say the weight is 11 newtons. Okay, now clearly the weight is 15 newtons, so the upthrust must be 4 newtons. And if you got the weight of the water displaced, it would be 4 newtons. And that is Archimedes' principle described. No calculations required at all. They're not allowed. It says in the syllabus, calculations on Archimedes' principle not allowed. So know the definition, know the experiment, and just for your own sake, kind of have the idea around it. We also have to mention very briefly the law of flotation. Okay, so I'll just sweep this out and we'll look at it. Okay, so for the law of flotation, we're talking about a special case when the body is floating. Now, if the body is floating, okay, think about it. It has a weight down. It has an upthrust up. Okay, the upthrust is equal to the weight of the water displaced. We're happy with that from definition. But if it's floating, well, it doesn't matter if the balance is there or not. The balance isn't holding enough. If it's floating, the net force must be 0, because it's not going anywhere. There's no acceleration down or up. It's floating. So therefore, the weight of the body, so this is the weight of the water, this is the weight of the body. The weight of the body must be equal to the upthrust, which is equal to the weight of the fluid displaced. So for the law of flotation, that's the situation. So if you had, let's look at figures. I can't remember what they were. Was it 15 newtons? If we took the same iron block. Okay, if it's floating, this will read 0 newtons. Okay, and the weight of the water displaced will be 15 newtons. Okay, so the weight of the body will be equal to the weight of the fluid displaced. That's the law of flotation. It's just a special case of Archimedes' principle, but know the definition. Okay, second thing, Archimedes' principle is the first thing, Boyle's law. Okay, and we look at Boyle's law in an experiment in a second, where we have pressure by volume is constant. Now, it's for constant temperature for a fixed mass of gas. Pressure by volume is a constant, or if you like, pressure is constant times divided by volume, or constant times 1 over volume. If it's equal to a constant, it's proportional to, if you make the volume 6 times bigger of a gas, the pressure gets 6 times smaller, and so on. So Boyle's law operates for gases. Those of you in chemistry, take that a step further with Charles' law and PV and NRT and all that, but those that's not in chemistry, we don't have to worry about that. All we have to worry about is that and the experiment on Boyle's law, which we'll be looking at in one moment. Okay. And finally, the third thing, so Archimedes is the first principle, Boyle's law, and the third thing is the pressure at a depth in a fluid. Okay, so as you go deeper into a fluid, well, if you think about it, okay, if you're down here in water, or if you're here in water, now it should make sense. There's more pressure when you're down here because there's more water above you than there is here. Okay, so pressure increases with depth. Okay, it increases with depth. It also increases with the density of liquid. The denser the liquid, the greater the pressure. Again, if the liquid is denser on top of your head, it's going to be greater. Okay, right. And it also depends on the acceleration due to gravity, because it's linked to weight. Now, we have a formula here that we just have to accept, okay, and just be able to use. P is pressure, rho is the density of the water, G is acceleration due to gravity, and H is the height. Okay, D is rho GH. Okay. It's to do with the difference in the force. We could cut through the maths. It's to do with the difference in the forces between the bottom and the top of the body. Okay. We're not going to do it. Okay, because it's not on this syllabus. Okay. So, but be able to do the calculation. There's going to be one calculation in our lesson now, and will be that. So it'll just be a 30-second job. We'll look at that in a second. Okay. There you go. Very good.